Hello everybody, we'll get this webinar started. Today we have Jon Wilde. He's part of our product support team over in England, and he's going to be presenting on car part smoke extraction and visibility, including best practices. He has a lot of interesting topics to cover, as well as results from customers that gave him permission to show the results. This is actually the first of a sort of transition of how we've been doing these webinars. In the past, we had singular events, and we kept inviting you every week or every month. And now it's going to be an ongoing series, so now that you signed up, whenever there's a new event, you'll just get an email letting you know that it's been added to the calendar so you can come and join. So, Jon, can you go to the next slide? So this marks the 10th CFD webinar. We started these back in February of this year, and you can see all the different webinars that we've done to date, all of which are on YouTube to watch. And as you know, you've probably all received this by direct email in terms of announcements, but if you want to know what the schedule is moving forward, it will be within the forum post that we manage for each of the webinars. If you're looking to download the actual slide deck or any other files that Jon makes available, there's a link in that previous slide that actually shows where you can go to autodesk.box.com/CFD10. So the number is just incremental with each webinar that we do. So you can easily go back to previous ones to see if there's any shared files available. In terms of any knowledge-based articles that have been developed in the past month and made public, we do a lot of internal non-public articles that we also write. But there are 5 articles there. If you download the presentation, you can look through each of these articles and see what other people are running into in terms of how-to questions or troubleshooting tactics that we provide to everyone out there that uses software. So at this point, Jon, I'm going to hand it over to you as this should be your agenda slide. And again, I want to thank everybody for coming, as well as if you have any questions throughout the presentation, please write those questions into the questions window, and myself and Caitlin are in the backgrounds, and we'll try to answer those live, or we'll bring them right to the front to Jon so you can try to adjust those to everybody. At the end, we will then do an open Q&A. You can ask us anything that you like, from CFD to Autodesk or anything, and we'll try to respond to that question as best as we can. So take it away, Jon.
Thank you, Royce. Hi, everybody. So first I wanted to just explain what we're doing and why we're doing it. And this is, I think previously I ran a best practices focusing on rotating machinery. And all of the support team, as far as I know, especially myself, have managed to use it so widely through a lot of cases that have come in. It's been so useful for customers. I thought I'd kind of carry on the best practices presentations that I'm doing. So a little bit more in a second about why. And the rest of today's agenda is going to be really the process of running a smoke extraction model from CAD, so taking a car part model into CFD, running through the main kind of setup points. I'm hopefully trying to capture everything that you need to do to run these models successfully. Then I'll talk about some of the results. And again, at that point, like Roy said, I've got some customer results as well that I've got permission to share. They're much kind of bigger models than we would typically demo, so they're very interesting to see. And then I want to talk about some pitfalls as well. So sometimes when you run these models, you find problems with error of divergence, and I want to cover a bit of that there. Okay, so why talk about smoke extraction? Honestly, it wasn't something I thought about presenting before, but it has been requested on so many occasions through support cases to myself, through the forum, and through questions, through past webinars. We thought, great, let's do it. There's obviously a large need. The smoke and visibility was added to Simulation CFD quite a long time ago, purely as a customer-driven enhancement. So all of the comments that you're making on the idea station, do get listened to, and this is one of the things that got asked for so many times by customers. and it's been growing massively ever since. I guess from my point of view, it really kind of focuses on human safety. So it would enable us to look at the path of the smoke from a fire, the visibility of a person from different points in the model. So that really is kind of telling us how far that person can see and whether they can see a sign that will help them to escape. If we're running a transient model, we'll get an idea of the time taken to entirely clear the area of smoke, giving us an overall understanding of the survivability of the fire. So starting with a CAD model, I would just like to say, actually, I'm not sure if Rockers is on the call, but this model is from a support case that we've been running recently from a company called Smits in the Netherlands, and they've said that I can use this model, and the results that I've got to show later are really impressive. They're very happy. And it's a nice model because it's pretty complex and it covers all of the main points that you need to run one of these models. So just kind of looking at the typical types of things we need to do. On the left-hand side of the model, we've got an inlet, and as inside we have jet fans moving the air. The inlet is just a zero pressure, so it's just open to the environment. And we have a scalar 0, which represents our 100% clean air, and we also have an ambient temperature. On our outlet, there may be multiple outlets. We would typically just have a zero pressure, so again it's just open. So there's nothing driving the flow other than the jet fans when they turn on. So they normally wait until the fire is sensed. So in the middle of the model we have a fire source. On that we would have some kind of volumetric heat load applied. That always is applied to the volume, and it's normally provided within a specification. It's often transient as it ramps up over time. And on top of that fire volume we'd also have a scalar of 1, so as air passes through it, becomes 100% smoke. And then at some point the fire would be sensed and the jet fans would turn on, and then obviously the flow would start to be moved from the inlet down towards the outlet. This is really following the first of our kind of two approaches. So the left-hand approach there is our standard approach. Everything is as in the model before. What I should mention as well is that we've got a resistance part, and that's our fire, and that's surrounded on either side, or around all of its sides, by a solid part, and that would be suppressed from the mesh. The idea being that the flow is always brought in the bottom as totally clean air and always leaves just the top surface as totally smoke. And then on the right hand side there's an alternative approach, and this can be used if in the specification you have a specific mass flow rate and a specific temperature from the fire. So the setup is very similar to before, but we have an additional inlet at the bottom where we have our flow rate and temperature and our scalar 1. So it works in the same way in everything else, apart from we don't have a resistance, we have a flow driven from this point. So from a CAD model, we need to really focus on what we need in CFD. So really keeping things simple is the key. We also need the walls and any important geometry. We need some kind of cap to seal the volumes. So what we tend to do is draw an additional part on the inlet and the outlet, and then when we bring that model through into CFD, if it's 100% sealed, CFD will build that internal, often complicated air volume for us. We also have our jet fans and our fire source, and I'll go into a bit more detail about the specifics of their shapes in a moment. What I will mention is that it's worth making sure, or at least trying to make sure, that your walls in CAD, especially when you're working with Revit, aren't overlapping. Often very small overlaps can cause problems when we move into CFD. It's better to fix those, but as a workaround that's often worth trying, there are a couple of flags that I've listed there where we can enable a different geometry kernel, and we can also tweak the tolerance that CFD reads parts in with, so we can increase that tolerance so it would ignore very small overlaps. Okay, so once we are ready, we would move across from CAD into CFD. Our boundary conditions for our air domain are pretty much as before. So we've got our P equals 0 on the inlet, the scalar 0 on the inlet, and our ambient temperature also on the inlet. And then our fire part will have a scale 1 just sitting on the very top of it. So there's nothing too complicated with that kind of step in the setup. But what I would mention, I guess, is if we don't know from a specification what our heat load is, we normally do, and we normally apply that to the volume. And there's a couple of equations here that we can use if we happen to know a mass loss rate or perhaps the height of the flame in conjunction with the size of the fire, so we can get an idea of what the heat release rate or the energy. Okay, so once we set up our boundary conditions, we need to set up our materials, and I just want to talk a little bit about CAD as well before we do this. There's a couple of things relating to the fan setup. There's kind of two general approaches and also the fire. So with the fans, generally we have jet fans. They're quite large fans, able to move high volumes of air very quickly. And this is a typical fan. And we always simplify it down, so we have just quite a long shroud, which is pretty much as design and reality. And we have a solid cylinder in the middle representing the fan. We always have the fan recessed so that we have nicely developed flow, especially on the outlet, which helps to form that long throw from the jet. There's an alternative approach, one that's also used pretty commonly. And there's a jet fan shaped like this, and this would have on the right hand side where the inlet is a centrifugal fan, and we try to simplify that down a little bit in CFD, and we find that we get the same results just by replacing that more complicated centrifugal fan with a simple cuboid part. So we're still moving the same flow rate, and it doesn't matter too much what's happening on the inlet side. It's really what's happening on the outlet side that's key, and the shape of the outlet there and the mesh that we have is going to give us the accurate throw distance that we need. So before we set any of those specific kind of simplified parts in CFD, we need to assign air to everything, because CFD won't let us assign fans unless they're within an air volume. So what I do generally is initially select everything and make everything a solid, just so I know that I've got or captured any kind of small overlaps and small parts. Select the air. It's going to need to be changed to air variable, so where we've got environment on the bottom left there, we would change that to variable. That allows the density to change rather than be fixed. So as the air is heated up through the fire, the density will reduce and the air will rise. And then we can assign our fan properties. So we would use an internal fan material, and we would attach that to our fan part inside the shroud. If it's a cuboid part, generally, well, if it's a cuboid part, we would have a 0 rotational speed, because we don't want that cuboid trying to rotate. We get some quite strange velocities. If we've got a cylindrical part, we can have a rotational speed. That's fine. And then we just set the correct flow direction. We need to be very specific about the meshing. This applies to every analysis we run with any kind of simplified fan part or resistance part, which is essentially a filter. So the fan material must have a uniform mesh, and it must have at least 4 to 5 elements from the inlet side to the outlet side. And this is purely because it's pretty complicated physics-wise. We need to make sure that CFD is able to capture the pressure drop across it accurately and accurately move the correct flow rate from one side to the other. What I would generally recommend as well is refine the mesh around the outlet of the fan casing. It's where the most kind of complicated flow patterns occur, and also what I tend to do is either add a meshing region within CFD, or if they're at a strange angle, it's easier generally in CAD to have on the bottom right there a meshing region where we can refine the mesh to help capture that jet more accurately. And just to give you an idea of what that would look like, you can see that we're we're pulling air into the fan, into the shroud kind of fan box and the casing, and it's exiting out. And because we have that nice mesh, the jet is propagating as it should. If we didn't have that mesh, and if the mesh was pretty coarse, what we might see is the flow spreading out far wider than we would expect, and the throw generally might be quite a bit shorter. So once you've got the fan set up, the last thing to do is to set up the fire, and that is going to be a resistance part. I generally, once I've created this fire part, I would have it saved within my materials because we use them so often. These are set up with 85% open area in every direction, pretty high conductivity, so that heat from the bottom surface can transfer quickly and accurately to the top surface. And it's important also to always have the flow direction set to the vertical. It seems kind of academic to do that because the Fourier ratio is the same in all directions, but we've seen it can make a really significant difference to the accuracy of the results. Same process again applies to the meshing. So I just wanted to show what an automatic mesh can look like on a cut plane. So this is that same fire volume with an automatic mesh applied to it, and on the outside it looks great. You know, we've got 4 or 5 elements along an edge, and that's exactly what we would want. But if we don't press use uniform, that mesh isn't propagated through into the center of the volume because it's driven just by the edges. So we wouldn't have enough mesh through the very core of the fire. So it's always important to use a uniform mesh to make sure that we are capturing that properly. And then kind of moving out a little bit, once you've got the fire set up, this is a model with a car on fire, the engine bay. What we would probably like to do is make sure that we capture the flow around the fire accurately. And generally underneath the fire we've normally got a pretty small gap, and we need to make sure that any flow that's being recirculated or entrained and pulled in through the bottom is captured well, and I often use a meshing region to do that. The mesh on the right is far too fine for these types of analyses, but I just wanted to kind of show the differentiation between the coarse mesh and the fine mesh. So that pretty much covers up the main kind of setup with regards to material, but then we need to set up the solver correctly. So the first thing to look at, or the first thing to consider, is whether we want to look at smoke visibility, which is going to enable us to use a cut plane at the eye height of the people in the car park, just to get an understanding of how far they can see. And that distance will vary, or the importance of that distance will vary depending on what signage we have. So if we have a reflective sign, the visibility will need to be far longer than if we've got an actual kind of lit sign like you can see on the right, where the visibility can be a little bit worse and you can still see the sign. I thought I'd mention, I don't want to go into too many technical details with regards to the equations, but we can later possibly. It's worth mentioning, I think, that this is the value that we use to calculate the distance that the person can see. And we use that scalar value from CFD to calculate the concentration of particulates, which is then fed back into this equation. Always we would want to run these models as transient. Obviously a steady state analysis assumes essentially an infinite runtime, which can generally mean that which almost always burn for a finite amount of time, for say 20 minutes. And what we found is that we can utilize a flag to help optimize the solver process. So once we've got our time step chosen, we would then select a number of inner iterations, which gives CFD an opportunity to converge on that specific time step before moving on to the next. Often we might say choose 10 inner iterations, which can often be a waste. We might only need 3. If we use this flag, what CFD can do is, as it's iterating on those inner iterations on that one single time step. If the error is less than 5%, you can say, okay, I'm done, and move on to the next time step. You'll also find that in the summary file, once this analysis is complete, CFD will tell you how much time it's saved by using this flag. So a little bit more about the solver settings. Our model is going to be run for 20 minutes, so that's 1,200 seconds. You'll notice that time steps to run is set to -1, and that's going to seem pretty odd for anyone who hasn't run a transient analysis before. So generally our stop time is set to -1, and we select the amount of time steps that CFD will run, and it will stop when it's converged. Here we don't want to do that. We want to be very specific about the time we run for. So we set the time steps to run to -1, so it's disregarded, and we can run for 20 minutes. And then within solution controls, almost always we return the intelligent solution control off, so that CFD is fixed rigidly to the time steps that we've prescribed. We would use Advection Scheme 5. And then when within result quantities, we return on visibility and set out smoke visibility parameters. And there are 3 parameters here, and I've given a few examples of what those numbers can be on the next page. They depend on what's burning. They depend on the types of signage that you have in the building, so whether they're illuminated or reflecting, and they also depend on the type of combustion. So just a quick summary of what we're doing. This is our model. There's nothing more complicated than this really, where it's just open on the inlet and the outlet. We have a temperature on the inlet, and we have our heat source and scalar 1 on the fire. Because we're going to be running flow and thermal together to help us capture the natural convection, we need to make sure that flow and heat transfer are both on at the same time, and we would set our gravity in the direction, in the downwards direction, which quite often is a negative direction. You'll see there I've got 0, 0 and -1 because it's downwards in the Z direction. We also need to set a diffusion coefficient, and because we're running a scalar analysis, CFD essentially is looking at how 2 fluids that are very similar diffuse together. Our recommended diffusion coefficient, which is given there, is optimized really for smoke within air. What we found is that sometimes that can cause a little bit of solver instability. So we can, if we want to, double that diffusion coefficient to the 0.2 centimeters squared a second that's shown in the bottom right. Generally that has quite a minimal effect on the results, really because the smoke isn't really driven by the diffusion, it's more driven by the momentum, it's more driven by the fans. So we can generally improve the stability of the solver without having a negative impact on the accuracy of the results. Okay, so just to kind of round up really, now we've kind of gone over the setup, just to take a look at some of the results that we can see. And this is again going back to the car model. So we've got an engine fire. On the left hand side we can see smoke. So the red value is the high scalar value, so this is going to be close to 100% smoke, and the blue is going to be totally clean air. On the top right we can see the velocity. So there's no fans in this model, so the kind of highest flow rate is going to be as the air passes into the fire and raises pretty quickly out of there as it's quite hot. And again in the bottom right is a transient analysis, so we can see that over time the fire has been burning and the heat is rising and it's gradually starting to fill up and heat up the room. And then the important things we want to look at really are going to be the scalar in the bottom left, so that's our smoke, and in the top right our visibility. And how I've got it set is the red is the lowest visibility, so where it's totally red we're only going to be able to see a meter or two, where it's totally blue. We can see up to 33 meters. So it gives us an idea of where a person in the room and how far a person in the room can see. Generally what we would do is place a cut plane at the height of the eye level so we can get a really quick global idea of the levels of visibility throughout the entire domain. We can then take a look at some ISO surfaces. So on the top left, this is after a certain period of time, the smoke being emitted from the fire, and there's a tiny animation in the bottom there which is showing us what happens over time. So the smoke, initially we have totally clean air in the model, and then over time that room is going to fill up with smoke. What I want to quickly talk about are some pitfalls, and you can see one just on the right here. We've got a really strange blob of smoke, and there's no fire on that side. If we see things like that from our analysis, generally it means that the mesh isn't quite as good as it should be. So it can be two things really. Either the mesh isn't fine enough, or the boundary layer is too thick. So I've just mentioned that at the bottom of this page. So we can either enable mesh enhancement blending, which is within the advanced function of the mesh, or we could just try refining the mesh globally. There's a few other possible pitfalls as well. I would say that almost always when a customer comes to us with a car park analysis, it's diverged and they don't know why. So if they followed all these steps, there's a few other things that could be a problem. One is that our P equals 0 openings, where we've got a pressure, temperature, and our scalar. If we have flow traveling in two directions over those openings, the same goes for the outlet actually. That can often cause solver instability. So we need to make sure that the flow is really only going in one direction. If it's not, we should probably extend those outlets to make sure that any recirculation is completed before reaching the boundary condition. Quite often we want to run these models for 20 minutes or more. If I was running one of these, I'd want to run a time step of maybe a minute and run 20 time steps and I'm done. But because so much is happening over time, the flow regime is constantly changing, we just can't do that. We need a pretty small time step. I'd say that almost always if we had 0.1 of a second, the solver would be okay and we wouldn't have any divergence. And that's obviously going to need a lot of time steps, so maybe increase that to 0.25 or maybe half a second. But that gives you an idea of the starting point. I would always start with a very small value like that. And again, I've mentioned the poor choice of diffusion coefficient. So if we're getting convergence but the solver looks very choppy and unstable, if we know the mesh is okay, then we may need to try that high diffusion coefficient to hopefully smooth out the run. And finally, I just wanted to share a couple of customer examples. One you've possibly seen before. I know it's been on our website. This was a company called Morsons who were looking at firing. It's called a granary warehouse, but it's actually a very large office. And obviously we've got the ignition point at the bottom of the screen there, and then over time the fire is spreading out and we're just trying to get an idea of where the smoke travels to, and then from then we could try to add fans, add smoke extraction to get an idea of how best to remove that smoke. And then a case that I ran recently, and the images that I've shown a few times through this model. This was one of the models that we ran for 20 minutes, and we had a fire. You can see on the top left exactly where that started, and you can see over the 20 minutes our room was filling with smoke and our visibility was gradually decreasing. So the blue is where we've got good visibility, but we're gradually seeing yellows and oranges and reds as the visibility decreases. Our customer also kindly provided us with a really nice video to demonstrate this. So we can see over time we have jet fans in the model, so we do have some kind of forced convection trying to move the air, but this is the visibility and how it changes over those 20 minutes.
Yeah, John, it's really cool when you look at these results, how the air rushing in through the hallways does a really good job to at least maintain a pretty open end effect, so that if people at least get to the ends of the car park, you can at least find the entrance and get out. So that, I find that really interesting, how well that really controls the smoke and keeps it essentially located.
Yeah, that's a good point. I think that's really clear, and that's why the whole thing isn't full, because we do have these very, very clean areas, like you say, and that's exactly right.
You can just see how that smooth pattern, especially on the left-hand side, it just shows what their design is trying to do there with the car park.
Exactly. Thanks, Forrest. Good point.
Mm-hmm.
That pretty much covers the setup and the results that I wanted to show. Finally, what I did want to mention is something that we found in the Autodesk labs, and this is Project Scorch. So this is, you can download this and you can test it out. It's a free technology preview, and we're actually using FDS, but with our front end, so hopefully it's a little bit easier to use, a little bit user-friendly. If I just move this along to a bit further in the model, what we can see is that we're trying to accurately capture what happens when we have a real fire. So in CFD, we're not actually modeling the fire, but we're trying to do our best kind of way to model it. Here we are modeling the fire, and you can see that effect as the smoke is produced and how it dissipates.
Yeah, so FDS, for people who aren't aware, it's Fire Dynamics Simulator. It's actually a U.S. government built solver. It's in the public domain. So there are various companies that sell it with front ends and then leverage the solver in the back end.
It looks really nice. I don't know, have you had time to play around with it, Royce? I know you were going to look.
No, not this week. Maybe closer to the holidays where things slow down a little bit. I'll get time to play around.
Yeah. Okay. I would say that covers everything I wanted to show. Hopefully I've captured the process as best as I can. Does anybody have any questions?
Excellent. Thanks, John. Not too many questions have been coming in. There are a few there that we're able to answer right off the bat. Remember, if you want to ask questions on smoke or any sort of AEC type of model, or anything at all, really, you're welcome to ask, and we'll try to respond.
I guess it's possible that my presentation was just too good and I just covered everything that's possible to ask. There's always that.
You always like to dream that, right? Should add this material to samples. So we had Sazo. It's a great detailed presentation. Should add this material to samples. So I'm guessing to the help material is what you mean. Yep. So
yeah, I guess that makes a lot of sense. I don't know what we do actually, Royce. I mean, I know that this will go on our knowledge network, so it will be in YouTube, and through an article, this will be available. As for putting it in the help, I don't know, that's a really good idea.
Yeah, I would forward it to Len, and so they can incorporate it. Because there's some help material on smoke analyses. It probably hasn't grown significantly since we first put it out there, so it probably would be really good to put some of the troubleshooting tactics right in the help. Because it can be sensitive at times to run these models because of how much is really going on with that high heat load from the fire, with the scalar analysis, capturing the smoke, and everything else.
Yeah, yeah.
Yes, it works fine with slip symmetry, Paul. That's completely, okay. If you had a large room with a fire in the middle, then you could theoretically cut it in half. Just realize that it's really not that symmetric. It's very much a transient analysis, but it will work. What I mean by that is that there will probably be some oscillating and biasing flow around the symmetry.
I guess what's worth mentioning is where it wouldn't work is if we had, if we were modeling radiation, we couldn't have more than one slip symmetry, right?
Right, for the most part, as long as it's periodic around that slope symmetry, because what we do in the background when you set up a true radiation model is that it does rebuild that mesh to develop a full model to calculate all the view factors. So if it can't accurately replicate that on either side of the slope symmetry, then that will fail.
Yeah.
Normally the half symmetry is pretty successful. Then when you start splitting it apart, it can start getting a little confusing. Has this method matured over the years? It has matured, and various code requests have come through with cases to add more stability. We've learned as well in terms of how to best approach these analyses from when it first came out. So yeah, I would say it's matured. If I'm not really sure what the intent is of the project Scorch, but that would also give another level of maturity, because that's a very mature code base, FDS, and would actually model the true, model the true burning of objects. So if you look at FDS, it's an interesting code, but using it out of the box from government labs is supposedly pretty difficult.
I'm going to let you think about Scott's question, Royce, while I talk about Sean's. Sean asked if we can visualize the smoke development as a color that represents smoke rather than the red and black, and we can. I've got it on the screen now. So basically, once you've got a cut plane in the model, this cut plane is showing Scalar. We can right click on the legend and go to options, and we can change that color pretty easily. So generally it's set to normal, but if we change from white to black, what we'll find is the smoke is black and the clean air is white. So that's the best way to do that.
And you can do a similar thing with ISO surfaces, and you can turn on transparency in those ISO surfaces so you can get an idea of how that progresses through the model. Sometimes that can be pretty heavy on the graphics, but we'll see how that works out with this model. Yeah, so this is kind of Sazo, that's a good question when it comes to solve time. So if you have a high-end desktop machine, running locally, most likely if you're just running a single analysis, it will solve faster on your desktop than it will in the cloud. In the cloud, in the current configuration that we have, because we use the Amazon cloud services, the current configuration we have isn't considered like a extremely high-end desktop platform. It's probably like I bet the hardware is probably a year and a half old, and if you look at the scheme of things, it runs very well, and when I use the cloud, it's usually to leverage multiple runs. So if I had 3 or 4 different designs that I wanted to interrogate with the cloud, then yeah, the cloud's going to win out then, because I can run them all at the same time. Okay, so that's really the intent there. Humidity and air with regard to dew point and possible sites for condensation. So are you trying to mix the smoke with humidity? Is that what you're trying to get at, Scott? I'm not quite sure what the question is. So scalar methods for humidity and air, has this matured over here? Oh, okay, I see what you're saying. All three of those kind of go together. Yes, actually, in terms of running humidity models, that has matured over the years. In regards to dew point, we don't really report on that, but sites of possible condensation, we do report on % liquid that is building up on walls. So if you were to do like an atrium design, which we have quite a few customers that do that, and you're trying to design the venting on the floor to control the air, the hot air going up the glass, in other words, yes, we definitely have people that do that fairly successfully. Does that answer that question, Scott? Great.
Cool. What I would also add, just to go back to the cloud question, the simulation that I have on my screen at the moment, I ran, I think there's a significant number of time steps saved. I did run it on the cloud and locally just as an experiment, And I think the runtime is pretty similar on both, but the problem with the cloud was the download. So I've got about 30, 40 different time steps, and they'll need to download. So that's why it was a bit quicker to run it on my desktop.
That's a really good point.
One thing we didn't talk about actually is animations. We can do that on this model. So at any point, once you're within your results, if you want to animate over time, we can just switch to animation and then select, I won't select them all because it will take quite a long time, a number of points, and then press animate. And now we wait. So what this is going to do is going to show us, or move basically with the view that we have, so that's showing quite actually low scalar value, progressing from time 0 to 20 seconds. And we can change the frame interval, so generally CFD takes quite a long time to get from one interval to the next. If we lower that a little bit, and we'll see that spread out much quicker. We could also change the colour if we wanted to, so we can see it a bit clearer. So you can do all this on the fly and it will keep animating as you go. And you can also, like I did for the PowerPoint I just showed, save out an MPEG or an ADI file. So it's nice and easy to do that, and save it and share it. And hopefully what you can see as well is it's not just the ISO surface, but it's the cut plane. So any vectors we had on a cut plane, whatever we had shown, that would animate over time.
Hey John, can you turn on let's stop the animation and turn the mesh on the cut plane you have right there?
Yeah, one sec.
Okay, and let's just go. Yeah, there we go. So Hoy, this is the kind of mesh that John ran with this model. And one thing, there's a couple of key points to look for when you have these defined plumes. If the plume ends up being very, very much following the mesh edges, so if we were to kind of take a side view of this, John, and if you were to look at the contours of that along the outside, if that plume started to follow those edges, that'd be one key signature that, yeah, you definitely don't have enough mesh there, because the flow is actually following the edges of the elements. Okay, so that'd be step one. In terms of do we have enough, that's always hard to find when it comes to CFD. Normally, when it comes to these kind of plumes with fires, I end up generally trying to overmesh. So you can see how in the actual fire zone itself, how tight that is. That is mostly due to all the heat that's being pumped out of that fire. So trying to get enough mesh in there so that it's very stable as it goes through the, a lot of times there's a transient heat up curve that people like to plot here. And more mesh usually helps. Now, because there's such long run times, it ends up being a balance game of, you're not trying to get dead accurate results here. You're trying to get an understanding of smoke control, of where it's really flowing, and just getting enough mesh to get a fairly qualitative view of what's going on is many times the goal with these kind of analyses. So in this case, it does a very good job of allowing the hot plume to rise and then reach the outlets that are defining the model. Okay.
I'd say that my mesh was too coarse here. I mean, my main focus was to run a model that had some good results that I could show everybody. But if we take a look, as a general rule of thumb, with any CFD model, that through gaps we want at least kind of 4 or 5 elements from one face to another, as a general rule. And if we take a look at the bottom, just underneath the car, excluding the boundary layer, we've got 2 elements. So our mesh is probably half as fine as it should be, and that we can follow that, and we can see the plume, like you say, Royce, it follows very much the lines of the elements. So really, it needs to be a bit finer, but it's going to give us a good idea.
Yeah, it'll definitely give you a good idea, and you know, it's a good starting point. You know, from here, what John would do if he was actually running this for work, he'd probably add in a refinement region in that plume, and then rerun that job. Now that he knows that the analysis is stable, and just to make sure the results for what he's trying to learn from the analysis isn't really changing. At least then he's got some preliminary results, and then he'll understand if more mesh is really necessary for his goals.
That's exactly right. Yeah. We can see with ISO surfaces, I mean, I know this looks pretty terrible, but there's a reason for showing it, and that's because this ISO surface is hugely driven by the poor mesh as we move away from the fire. So there's, you know, blobs that if we refine the mesh wouldn't be there anymore, and this would all be much, much smoother. But for the sake of what I wanted, and probably for most analyses, it's okay.
Yep.
Okay, I think we've
Hopefully
run through all of the
for
questions.
you. I think so.
Yeah.
So let's give it another minute here. One of our power supplies catches fire. Yeah, that'll be good.
What I will just share actually is, while we're waiting for any more questions before we bring the call to a close, when we're saving out MPEGs, I find that generally the frame rate is terrible, and they either occur really quickly or really slowly. And you could see the animation that I had in my PowerPoint was really, really fast. And if we can use a flag to control the frames per second in MPEG. So I've used a value of 8. Although when I click on it, it changed to 1. If we reduce that value, we should be able to slow the MPEG down a little bit. Just something to bear in mind, you know, if you're creating results and you don't want to share it this way, you want an MPEG that's a really small file that you can send around, then it's quite nice to use that flag to give you some power over the frame rate.
Good stuff. Well, no more questions really coming in.
Paul asked if I used any mesh enhancement tools. I didn't in this case. It is often really useful to use surface refinement, really because it helps with the control of the boundary layer if we've got very large domains, so we can minimize the kind of blobs that we're seeing with the ISO surface by improving the boundary layer without necessarily changing the mesh too much. So if we utilize that surface refinement, it can be really useful. But the gap refinement isn't so applicable here because generally there aren't any small gaps like a valve that we need to kind of focus our analysis around.
Hey John, did you use a manual or automatic mesh here? Seems very
I
structured.
used a manual mesh. You can just move up and check. Yeah, just a quick manual mesh.
Okay. Yeah, a lot of times manual meshes for these kind of analyses are handy because you don't really know necessarily where the flow is going to be going. This is probably many have seen as you use the automatic mesher, the core or the middle of these large rooms end up being extremely coarse, and that can sometimes be the instability points in your models. There's just too much mesh. You have all these different flow profiles going through. So sometimes sticking with a manual mesh, adding in some refinement regions near the hot fires for these kind of models, ends up being a great place to start.
That's an excellent point. Well done, Royce.
Let's see here. Any last questions that have come in? No, that seems to be it. Again, everybody, I want to thank you for joining. John, thank you for putting the presentation together. And we'll be looking to have these monthly on Wednesdays at 11 o'clock Eastern Time. And the schedule will be up on the forums, as well as you should get emails. And if not, please email us at autodesk.help.webinars@autodesk.com. And there's a few of us that monitor that email address in regards to anything on these webinars. As soon as this recording is up on YouTube, we'll send you an email and let you know that it's posted so you can share it around or rewatch it as you see fit. Thanks again, and we'll look forward to talking to you guys in about a month.